Okay, this is a video lesson for discussion 11.3, which focuses on Taxol as a specific example of medication that uses chiral auxiliaries and nuclear medicine. So this is D7 and D8 in the textbook. If I could impress upon you one thing about this, is that if you hope to do well on this part of the IB exam, you really need to read the textbook. I'm going to hit the highlights here, but that's about all I can do in this video lesson, so you may want to read the textbook to help give yourself sort of the bigger picture. Okay, so what is Taxol? So Taxol is a drug that's used to treat several different forms of cancer, and it naturally occurs in yew trees, but it occurs in really, really small amounts, so this is not sufficient to meet demand. So initially, a synthesis of Taxol was attempted that involves 4 basic steps. First, they extract the yew bark and the stem with ethanol, and that's to try to remove all of the Taxol that's present. Then it's concentrated and partitioned with water and chloroform. So basically, because Taxol is really insoluble in water, it goes into the organic layer, the chloroform layer, and then we can isolate it from other substances that are present. And then basically this extraction is repeated over and over and over again to try to increase the concentration. And this is called multi-step partitioning. Now, the product is almost insoluble in water, therefore it can't really be administered via an IV. So there's a lot of limitations with this synthesis. It's incredibly time-consuming. It's got many, many steps. That repeated extraction is a lot of steps, and it produces very, very little, and then the product's not soluble. So to try to combat some of these challenges, there's now a semi-synthetic process. So rather than trying to isolate the Taxol directly from the yew bark and stems, now it's isolated from the leaves of yew trees, but instead of getting Taxol itself, we're looking for a precursor of it. So this has a much, much higher yield than getting Taxol directly. It's about 50 times higher if we get the precursor for it. However, if we're only getting the precursor of Taxol and not the Taxol itself, then we're going to have to do some reactions to turn that precursor into Taxol. So then there's a series of reactions used. You don't have to know them. They do include condensation reactions, which you should know, but you don't have to know all the specific reactions. And in the development of this process, they were also able to resolve the low solubility issue by mixing the drug with castor oil and ethanol and then diluting it with saline. So that allows it to be administered via IV. Now, there's a lot of challenges in the synthesis of Taxol starting from this precursor. Now, synthesizing it from the precursor did solve some of the problems, but there are a couple challenges. So the first thing is that to produce Taxol from the precursor, the side chain, which is this over here, has to be synthesized. Okay, now, this side chain contains 2 chiral carbons. So I'll try to, it's the one attached to the amido group here, and then the one attached to the hydroxyl group here. So this is a big issue in synthesis, and we talked about this a little bit back in Unit 10 when we were talking about chirality and how when substances with chiral carbons are made in nature, only one enantiomer is produced, but in the lab we typically produce a racemic mixture. And we talked about thalidomide as an example of a place where that was incredibly problematic because one of the enantiomers had terrible side effects. So that can obviously be a big issue. These enantiomers may not have equivalent effects in the body when they participate in biochemical reactions. So what we're going to do instead is use something called chiral auxiliaries. So chiral auxiliaries are just basically readily available chiral reagents that I can temporarily introduce and attach to a substrate and then remove it when the synthesis is complete. So this is sort of a brief overview. I start with my substrate, so my precursor molecule, okay, and this is a non-chiral molecule. Then I'm going to attach my chiral auxiliary, which I'm abbreviating as A, and the star there indicates that it's chiral. Okay, so I'm attaching that chiral auxiliary to my substrate, and because I'm starting with one enantiomer, I'm only making one enantiomer here of the substrate with the auxiliary attached. Now, with the auxiliary attached to the substrate, I'm going to add whatever reagent or reagents are needed to produce my product, and then I'll make my chiral product that's still attached to the auxiliary. Now we'll talk about the significance of that in just a second. Then I'll remove my chiral auxiliary and I'll be left with a product that is predominantly one enantiomer. So basically what the chiral auxiliary does is it affects the configuration of the product. It's really similar to biological processes where enzymes will temporarily bind and allow only one enantiomer to be formed. So we're sort of replicating the biochemical synthesis of some of these things. And we can do this isn't just with Taxol, we do this with other drugs as well. And it allows us to make some drugs with only one enantiomer. Now, we need to be able to assess whether we were successful at doing this or not. So first of all, we have to understand that small quantities of the other isomers will form. We're going to attempt to remove these based on small differences in physical properties, so solubility, melting point, etc. But then what we're going to do is test the purity of the final product using a polarimeter. So remember that enantiomers will rotate plane polarized light in opposite directions. If I had a racemic mixture, I would not see that rotation because they would sort of cancel each other out. So based on the degree of rotation, I can determine how pure my final product is as far as getting just the one enantiomer that I want. Now, of course, it's a very simplified version of how we do this, but that's sort of the extent of what you need to be able to understand at this point. All right, now let's talk about nuclear medicine. This is actually a huge area, and it's really interesting. There's a lot more on this in the textbook. Again, I'm hitting the highlights, but it's a really, I don't know if it's a fun read, but it's an interesting read regardless. So I would definitely encourage you to check it out to supplement what you're learning in class in here. All right, so we know that radionuclides emit ionizing radiation, and this is just radiation that has sufficient energy to remove an electron, right? And ionizing radiation isn't something that we generally want to be exposed to in our day-to-day lives because it can cause mutations in DNA, right? And so actually being exposed to radiation is a potential cause of cancer. So this radiation can be used to target cancer cells because we want to hurt cancer cells. So we can sort of use this damaging property to our benefit. So there's a couple different kinds of radiotherapy that are used. Brachytherapy is sort of internal, it's at the site. So radiation sources are inserted into the body, and this would be in the form of either metal wires or pellets that are going to deliver radiation directly to the site of a disease. And then external radiotherapy is when cancer cells are destroyed by very precisely directed beams of either gamma rays, protons, electrons, or neutrons. And later when we talk about alpha therapy, we'll talk about why alpha particles can really only be used internally as opposed to externally. They're also used for diagnostics. So basically, using a specific isotope, we can look at the nuclear emissions from the body, and these emissions are detected and processed to produce 2D or 3D images of internal organs. All right, so let's talk about types of radiation. Now, most of this should be a review from IB Chem 1, but you may have forgotten some of it. So alpha particles are basically just helium-4 nuclei. And you can either abbreviate them with the alpha symbol, or you can just write 4,2He because it is a helium nucleus. Since a helium nucleus has 2 protons and 2 neutrons, it has a charge of +2 and a mass of 4. A beta particle is an electron, and you can either use the beta symbol with a negative sign. You can also put a negative sign on the electron if you like, or you can just use a lowercase e to indicate that it's an electron. And it has a mass of approximately 0. Now, of course, an electron has mass, but in terms of atomic mass units compared to the mass of a proton or a neutron, it's nearly negligible. And so when you're abbreviating it in a chemical equation, you can say 0 for the mass, and it has a charge of -1. Gamma particles or gamma rays are just photons with no mass and no charge. Positrons, you can kind of think of them as anti-electrons. They have a negligible mass, same as the electron, but they have a positive charge instead of a negative charge. We know about protons. They have a charge of 1 and a mass of 1 atomic mass unit. And we know about neutrons. They have no charge, but a mass of 1 atomic mass unit. Now, you hopefully remember how to write balanced nuclear equations from IB Chem 1, but just in case you don't, we'll review that briefly. Now, the IB guide suggests that you only need to be able to write balanced nuclear equations with alpha and beta particles, so be sure that you especially know how to represent alpha and beta particles in an equation. All right, so let's look at an example of a nuclear decay. All right, so Lead-212 decays to bismuth-212, and when we're trying to figure out what other particle is emitted, we have to basically balance the equation. So remember that the sum of the mass numbers on both sides has to be equal, and the sum of the atomic numbers on both sides has to be equal. Okay, so lead has an atomic number of 82. Now typically that might not be given to you, but you should still be able to find it quite easily from the periodic table. And since bismuth has an atomic number of 83, we see that the missing atomic number here has to be -1. Right away that tells me that it's a beta particle, and we also see that the mass to balance the equation over here would be 0. Now, we can also look at two-step decays. So for example here, bismuth-212 decays by beta decay to polonium-212, and you could again fill in those bottom numbers. For bismuth 83 and polonium it's 84. And then polonium-212 decays to lead-208, and the bottom number for lead is 82. So we see that the missing particle there has to be an alpha particle. All right, so go ahead and try the last one to make sure that you understand. You could pause for a second, then check your answer. All right, so bismuth-212 decays to thallium-208 via alpha decay, and then that product that's formed decays by beta decay to lead-208. Okay, so you should be able to write those. A question might be asked, like, write an equation for the alpha decay of polonium-212, and you should be able to produce that. Okay. Sorry, that's my washing machine telling me that my laundry is done. It's quite a catchy tune. All right, so when we calculate nuclear decay, there are several equations we can use, and all of these are mercifully in the data booklet. So you don't have to memorize them, but you do need to know what things stand for, because the data booklet's not going to tell you that, and know when you might use them. So first of all, we have something called a decay constant, and that's related to the half-life, which you should know from IB Chem 1. It's the amount of time for half of a radioisotope to decay via this equation. So the decay constant is equal to the natural log of 2 divided by the half-life. Since we can obviously just solve for the natural log of 2, we can also just say it's 0.693 divided by the half-life. Now, we can also find the final amount of a substance given the time that the substance decayed and its initial amount. So you can use the first equation to solve for the decay constant, put in the time that the sample's decaying and the initial amount, and you can get the final amount. And also potentially useful, although I haven't seen it as much in some of the sample questions, is for finding the amount at a given time t, if you're given the rate constant. All of these are first order processes, so if you know the value of k, you can again find the amount at time t. All right, so let's look at a sample problem. This is a dose of a drug containing radioactive fluorine-18 is administered to a patient, and the amount of the isotope at the beginning is 1.5 times 10 to the negative 8th moles. We know that its half-life is 110 minutes, and we want to know how many moles of the isotope will remain after 90 minutes. So I would suggest, if you feel like you have some sense of how those equations might work, that you pause and try this, and then I'll go over it. We're going to use 2 of those equations that we looked at before. So you might want to pause and try it and then check your answers. Okay, so the first thing to do is to find the decay constant. So we can do that using the first equation, and we get that the decay constant is 0.0063. Then we can use our second equation. We know the initial amount, N0, that's given in the problem. We found the decay constant already, and we know that we're looking for the moles that will remain after 90 minutes. So when we substitute that in, we get that the final amount is 8.5 times 10 to the negative 9th moles. Now, let's also do kind of a common sense check. We know that the amount should be going down because it's decaying, and it is. And we also know that we have not had a full half-life go by yet. So it shouldn't quite be divided by 2, and it's not. So our answer does kind of make sense based on what we know about half-life and radioactive decay. All right, so let's talk about targeted alpha therapy. Now, Alpha particles actually cause more damage to cellular tissues within the body than any other form of radiation. However, we told you in Chem 1 that we don't really worry about alpha particles so much in our immediate environment, and that's because they have very low penetrating power. Your skin will actually block alpha particles. So that's why when we talked about the external radiotherapy with the precise beams of radiation, we don't use alpha particles for that because it would be blocked by your skin. So these are absorbed within a really short range. So what we can do is use controlled alpha emitters that are combined with some kind of a carrier drug or a protein that's going to go directly to the cancer cells, and then it selectively destroys them. This is particularly useful for dispersed cancers throughout the body, because if we can send the alpha emitters directly to the places where they're needed and they destroy cells within a really short range, that's helpful because it sort of minimizes the damage to healthy cells. There's also a technique called boron neutron capture therapy, and that uses high intensity neutron beams, and boron-10 has the ability to absorb neutrons. Boron's also used in nuclear reactors for this particular property. And so it absorbs a neutron to make a sort of intermediate boron-11 that then decays into lithium-7 and an alpha particle. So boron can be absorbed by the tumors, and once it's there in the tumors, it can be subjected to the neutron beams. So the reason this destroys the tumor is that once boron has been subjected to the neutron beams, it emits an alpha particle, which is then in just the right place to destroy the cancer cells. Now, radiotherapy does have a number of side effects. So possible side effects could include things like hair loss, skin and nail damage, nausea, fatigue, even sterility. It can also lead to the possibility of secondary cancers because healthy cells are also affected by the radiation. There's a possibility for further mutations that can lead to cancer. This could be years down the road, but it is a possible risk. There are damage to normal cells or surrounding tissue. So those are definitely things that people taking them should be aware of. And some of the side effects from chemotherapy are short range, but when we talk about radiotherapy, some of the damage to like hair follicles and skin and nail can be more permanent. So certainly it has some negative side effects, but we don't typically use radiotherapy unless it's really needed to combat something serious like cancer. All right, so I'm going to go through a few common radioisotopes and their uses. We're going to really focus in on one of them, but I want to go through a bunch. So technetium-99m, that lowercase m means it is metastable. This goes through gamma decay, and this is actually the most commonly used isotope in medicine. And it's used for lots of imaging: tumors, organs, bone, muscle, brain, biological fluids, really widely used, and we'll talk in a minute about why that is. Lutetium-177 undergoes beta and gamma decay. It's used for targeted therapy and imaging of small tumors. Yttrium-90 undergoes beta decay. It's used for cancer, brachytherapy, and palliative arthritis treatment. If you don't know what palliative means, it means that it relieves the symptoms but doesn't necessarily treat the underlying condition. Iodine-131 undergoes beta and gamma decay, and it's used for imaging the thyroid and other internal organs and for radiotherapy in thyroid cancer. And lead-212 undergoes alpha and beta decay, and it's used for targeted alpha therapy in cancer patients. And you should be familiar with at least a few of these, particularly technetium-99. That comes up a lot. All right, so let's focus in on this. Now, this is the most common isotope for medical use. Let's talk about why. The main thing that makes this so useful is the half-life. It has an ideal half-life of 6 hours. Now, different isotopes have half-lives ranging from nanoseconds to billions of years. And when we're looking at an isotope for medical uses, we have to really focus on that amount of time. So a couple reasons that half-life is super important. It's ideal for medical imaging because a very small amount of the isotope will produce enough gamma radiation in the period of time that we need it to image. If the half-life was much, much longer, it probably wouldn't produce enough quickly enough that we can get good images. And because it's only 6 hours, It's mostly decayed within 2 days, so that limits the long-range exposure to the radiation. But 6 hours is also long enough to prep the samples without it decaying away. It has multiple stable oxidation states, and it makes a lot of different useful compounds with different ligands. So those are just some of the reasons that this is a useful isotope. I would suggest reading more in depth about this and other important isotopes in the textbook because there's a lot there to learn. And again, I think it's really interesting. Okay, so in conclusion, read the textbook, come to class, ask me questions. All right, good luck.